Welcome to this explainer, where we're going to completely demystify Chapter 1 of the CM1 syllabus. Look, we all know this exam is basically the notorious gatekeeper of actuarial science, but today we're translating its dense math into a plain English survival guide. We're going to build a really detailed, step-by-step foundation of the time value of money so that you can tackle absolutely any problem this syllabus throws your way. Let's get right into it.
Okay, think about this for a second. If someone offered you a choice right now, £10,000 today or £10,000 in exactly 5 years, your gut instantly says, take the money now, right? But why? I mean, it's the exact same amount of cash either way. You inherently know that getting the money today is better. But as actuaries, we have to actually prove your gut right mathematically. We need to precisely measure exactly how much better today's money actually is compared to tomorrow's.
And it really all boils down to this. Money in your hand today has the potential to grow, whereas a future payment is honestly nothing more than a promise. If you have that 10 grand today, you can invest it, you can earn interest, and you can watch it sprout into significantly more than £10,000 in 5 years' time. This isn't just about inflation eating away at your purchasing power. It's about the pure mathematical opportunity of exponential growth over a specific timeline. And that potential? Well, it has a precise, calculable value.
So here is our roadmap for today. First, the actuarial alphabet. Second, moving money through time. Third, converting rate measures. Fourth, step-by-step worked examples. And finally, dodging common exam traps.
All right, let's jump straight into Section 1, the actuarial alphabet, where we're translating the math into plain English.
We really have to build our foundation with I, the effective annual rate. Honestly, if you don't speak this language fluently, the formulas later on simply won't make sense. So I is your true annual rate, with absolutely zero compounding tricks. When a formula asks for the effective rate, it means the actual proportion by which your money grows over exactly 1 full year, assuming the interest is paid at the end. For example, if I is 0.05 or 5%, every single pound you invest at the start of the year becomes exactly £1.05 at the end. It is literally the anchor point for everything else we're going to do.
Next up is V, the discount factor. I always like to think of V as a time machine. It's the exact decimal factor that you multiply by to shrink a future payment back into today's present value. If someone promises you £1 in a year and V is 0.94, that means their future promise is worth exactly 94 pence to you right now. Mathematically, V is calculated as 1 divided by 1 plus I. It's the core engine that lets us pull money backwards through time.
Then we have D, the effective annual rate of discount. Now, the absolutely crucial point here is to not confuse this with V. What D represents is the percentage of interest paid in advance. Just imagine you borrow £1, but the bank skims their cut off the top immediately at the start of the year, leaving you with less than £1 in your pocket. But catch this, you still owe a full £1 at the end of the year. That is a discount rate. Mathematically, it's very straightforward. It's simply calculated as 1 minus V.
Finally, we have delta, the force of interest. This one is my favorite. I call it the speedometer of interest. Imagine continuous, non-stop compounding. This speedometer tells you exactly how fast your money's moving at any given exact microsecond. Instead of interest being credited just once a year or once a month, it's happening constantly. You might be wondering, why do actuaries even use this? Well, in the real world, cash flows like life insurance premiums or pension contributions are coming in constantly, every single day, not just neatly on December 31st. Delta allows us to perfectly model that real-world fluidity.
Okay, moving on to Section 2, moving money through time. This is the engine of accumulation and discounting.
With our alphabet sorted out, let's actually look at the mathematical machinery. This is the stripped-down math of exponential growth. It's where your money and the interest on that money accelerates like a snowball rolling downhill. The formula is simple. Your accumulated value at time t equals your principal multiplied by 1 plus I, all raised to the power of t, which represents the number of years. That exponent is the secret sauce to the snowball effect. We use compound interest because it reinvests the gains every single period. Simple interest is just linear, and it completely breaks down mathematically over multiple periods because it ignores that massive reinvestment feedback loop.
And to reverse that whole process, this formula is exactly how we discount. We're untangling the growth by multiplying by our shrink factor to find the present value. You basically take your future cash flow, multiply it by V raised to the power of n years, or, which is exactly the same thing, divide it by 1 plus I to the power of n. Oh, and here's a really quick tutor tip for the exam. If your calculated present value ends up being numerically larger than your future cash flow, you've accidentally accumulated instead of discounted. So always do that quick mental check.
Let's dive into Section 3, Converting Rate Measures, also known as the shapeshifter.
We call rate conversion the shapeshifter because I, D, V, and delta are truly just different descriptions of the exact same interest environment. It's kind of like measuring temperature in Celsius, Fahrenheit, or Kelvin. The actual heat in the room is exactly the same, you're just looking at a different scale. Whenever you face a rate conversion problem, strictly follow these steps. Always anchor yourself with the effective rate I first. Let's do a super fast numerical example. If I is 5%, you immediately find V by calculating 1 divided by 1.05, which gives you a discount factor of roughly 0.952. Then, D is just 1 minus 0.952, which is 0.048, or a 4.8% discount rate. And finally, delta is just the natural log of 1.05, roughly 0.0487. If you master this step-by-step pipeline, conversions will literally never trip you up.
All right, Section 4, step-by-step worked examples. Get ready for the boss fight. Piecewise rates.
So let's tackle this complex boss fight. What actually happens when the interest rate changes midway through your investment timeline? This is where a lot of students panic, but the math is beautifully logical if you just follow the rules. You must slice the timeline into segments and chain the growth factors together. Let's walk through it. Say you invest £1,000 for 8 years. It earns 5% for the first 4 years and 7% for the last 4 years. First, calculate segment 1. £1,000 times 1.05 to the power of 4 gives you an accumulated value of £1,215.51. Now treat that entire accumulated amount as your brand new principal for segment 2. Multiply £1,215.51 by 1.07 to the power of 4 to get your final answer of £1,593.28. You're just isolating the blocks of time and chaining the multipliers together. And now for Section 5, Dodging Common Exam Traps. Welcome to the mathematical minefield. This is arguably the most vital part of this explainer, surviving the mathematical crimes that will absolutely cost you marks. Knowing the formulas is only half the battle, right? Knowing how examiners try to trick you is the other half. The single most fatal mistake students make is taking a headline nominal rate and plugging it straight into the accumulation formula. If an exam question says a nominal rate of 8% convertible quarterly, that 8% is a total fake headline rate. It literally just means 2% per quarter. You absolutely must convert it mathematically to a true effective annual rate before it ever touches your 1 plus I to the power of n formula.
Let's look at the severe punishment for that exact crime. We're talking about a massive 259-pound gap on a 12,000-pound investment just because the rate wasn't converted. If you plug a fake 8% directly into an 8-year compound formula, you'd get $19,042. But if you properly convert that quarterly compounding to its true effective rate, you find the real answer. How? Well, 2% per quarter means you calculate 1.02 to the power of 4, and then subtract 1, giving you a true effective annual rate of roughly 8.243%. Compounding that true rate over 8 years yields $19,301. That difference literally means a failed exam question. Always convert your nominal rates first.
Here's another trap to watch out for. Thinking you can just take the simple average of 2 different interest rates over a timeline. Never do this. Remember our boss fight a minute ago? If you have 5% for 4 years and 7% for 4 years, a huge amateur mistake is averaging them to a flat 6% and compounding that over 8 years. Because of the mathematical properties of exponential growth, averaging will mathematically always give you the wrong answer. It completely ignores the actual path the compounding took. Like we said earlier, you absolutely must chain the segments.
Before you hand in any exam answer, I want you to run this instant 3-second sanity check. As a golden rule, D is less than delta, which is less than I. Look at the full inequality string. D is less than a nominal discount rate, which is less than the force of interest, which is less than a nominal interest rate, which is less than the effective interest rate I. Because D takes interest out at the very beginning of the year based on the future amount, it is numerically the smallest percentage. I pays at the very end based on the starting amount, so it's always the largest. And delta is continuous, so it sits perfectly right in the middle. If your calculator ever tells you D is larger than I, stop right there, you for sure made an arithmetic error.
So, you now have the foundational bedrock of actuarial math. We've learned to perfectly move a single guaranteed cash flow forwards and backwards through time. But think about this.
How will these precise tools actually hold up when we introduce the absolute chaos of human mortality and multi-decade variables? Because soon in the syllabus, we're going to need to apply these exact same discount factors to pensions that only pay out if someone survives, or life insurance that only pays out when they pass away. That is where actuarial science gets truly fascinating. Thanks for joining me on this explainer, and definitely keep practicing those step-by-step rate conversions.